Good evening, class. This is Mohit, and this lecture belongs to NPTEL Quantum Hole Effect 2025 semester. And in today's class, I'll be discussing about the tight binding model and the related stuff. We'll wait for up to the 6:05, and after that, we'll start the class. Yeah. So this is NPTEL Quantum Hole Effect course, and this is the class 4 of the TA assignments. And in today's class, I'll be discussing uh, about the time binding model, the need of it, and a brief intro to it. Then I will talk about the graphene, which is a 2D material and made up of the carbon. Then I'll go on discussing the tight binding dispersion of the graphene, and then seeing the dispersion near the Dirac points, how it looks like. And in the later of the part, we will see the density of states behavior of the graphene, how the denser state evolves as a function of energy in graphene, and the later we will introduce the magnetic field in a square lattice, and we'll see how the tight binding model evolves in that case. This is essential in understanding the role of the magnetic field in presence of periodic potentials that eventually leads to this Hofstadter butterflies spectrum, a fractal spectrum, self repeating spectrum basically. And in this class, we'll discuss the tight binding model. And in the last section of the class, we will discuss how we can introduce the magnetic field in the tight binding model through the chiral phase, and that leads to eventually in the Hofstadter spectrum. So, having said that, I'll start with the uh, need how the bands are formed basically, the picture. So, the bands we have seen that the bands form from different perspective. Like for example, in the free electron model, we take electrons to be free, they are not attached to these atoms, and then they just uh, they are free electron. They have the spectrum of h bar square k square by 2m, right? But with that model, you can't explain the Dirac nature, the linear band nature of the charge carriers in case of the graphene, which has the Dirac spectrum. So we need some models which is quantum mechanical based, and that can give the more of the realistic results which we observe experimentally also, and they should be more close to and they should also boil down to this free electron model results also. They should satisfy those results. And having said that, so in the picture of the bands from different perspective, so the bands, electronic bands, have different perspectives, right? We have seen in the free electron model, Drude model, basically those models, then the Crony Penning model, how things evolves, and so there can be different perspectives to understanding physics. So there is a molecular perspective to it, and that's what we call the quantum mechanical also perspective, in which there is a mixing of atomic orbitals. We know that if there is an atom, for example, I'll just take a simple model of diatomic molecule, and then we'll add more of the molecule to show how, what, and how things change in these molecules. Because essentially, that's how a material is made. It's made up of multiple atoms or molecules, right? So if you have like two atoms, if you have an atom and you have another atom, they are very far kept away so that they are not interacting. And now if I ask you to draw the energy levels in the quantum mechanics, we know that the energy levels are discrete and so on. They can be on the top also. So this will be the ground state, then the second. And in these states, these electrons resides. This we know from the quantum mechanics. And similarly on this side also. This is the case when the electron is bound to this atom. Here the electrons are not free. We have asked them to, we have basically constrained them to bound to the atom, and then we have drawn the energy levels. Now what will happen if you bring them these two closer? The electron of one and electron cloud of one atom and another atom, they will start interacting, and there is a Pauli exclusion principle which says that the electrons can't be in the same quantum state. So the energy levels will split. One will go up and one will go down. So what essentially will happen will be your atoms will come here closer, and just to show some bonding between them, I'll just draw this line. They are so near that now the interaction has started. And now if I ask you to draw the energy levels, what will happen? This n equal to 4 level will get split into 2. Similarly, n equal to 3 level will get split into 2. The high energy one is known as the anti-bonding, and the low energy one is known as the bonding. So this is anti-bonding, and this one is bonding, right? And This is the case if you have the two atoms and you bring them close, right? But now if you can similarly think of, you can have like n number of atoms, how the things will change. So in that case, if you have the similar structure, let me just draw multiple atoms where you have this atom here, this atom here, this, they all are equally spaced. For time being, I'm drawing it like that only. And here, 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 here. Let me just bring it slightly down. These are the atoms. Now, if you bring a third atom close to it, there will be split of three levels, right? Similarly, there will be multiple splits. So I'm just drawing n equal to fourth Landau level. So on the left, you are having n by 2 atoms. On the right also, you are having n by 2. So total n number of atoms are there. If you are bringing them closer, let's draw for n equal to 4, small n equal to 4 levels, right? So I'm drawing n equal to 4 levels. What will happen? If you see n equal to 4, for two atoms, one will go up, one will go down. If there is another atom, one will go up, one will go down, one will go up, one will go down. They'll be like this. And how many of these? If there are two, there will be two. If there are n, they'll, if there are n by 2 on the one side, there will be n by 2 on the bottom. So here these will be n by 2 levels. On this side, this will be n by 2 levels. And what essentially it is, on the top side which you are seeing is like conduction band. On the bottom, it's like a valence band. And this is like orbital. This belongs to the bonding orbital, which has the lower energy. And this belongs to anti-bonding orbital, right? Now, similarly, n equal to 2, 3 levels will also be split, and from the high energy bands, right? So this is called n equal to 4 I have drawn, but 2, 3, 1, all, and n equal to 5, they will also split. And that's how the bands are formed. But if you see the microscopic picture, what essentially happening is the linear combination of atomic orbitals, right? So in the back end, the channel, the thing which is happening is linear combination of atomic orbitals. So I'll discuss these results and they will eventually boil down to the tight binding model. So please bear with me. We will land at the right point. So you have the linear combination of the atomic orbitals. Now, what do you mean? You have one atom here, you have another atom here. Now, if I ask you, write down the total wave function. For example, this one has the wave function atom. This is my atom 1, this is my atom 2. So when I ask you to write the linear combination of atomic orbital of the molecule, what you will write? It will be A times, where A is some constant, atom 1, its position R, plus B some constant. A and B are chosen such that to they normalize the wave function, and this is for atom 2, right? And now A and B can be, if they are the symmetric atoms, I'm taking that to be the symmetric atom, like for example, the carbon only. In that case, homonuclear molecule, I will call that a homonuclear molecule. In that case, your wave function can either take value, because then your A and B will be, the absolute value of A and B will be same, right? And that can give you the two combination, psi atom 1 R1 plus psi atom 2 R1. So this we know from the chemistry class also, that from the quantum mechanics, that this is bonding orbital and this has lower energy. And then there can be another one which will be psi atom 1 R1 minus psi atom 2 R2 R, and this will be anti-bonding. and they lead to the splitting of these orbitals, right? So if you had your two atoms here like this, what essentially you are doing, you are breaking the energy. One will go up, one will go down energy, and this will be psi anti-bonding, which will be psi 1 minus psi 2, and this will be psi bonding, which will be psi 1 plus psi 2. This scale is energy on the y-axis. So this is linear combination of atomic orbital. This is linear combination of atomic orbitals. Now, since you have seen it for the two molecules, I can ask the question, can I form a crystal orbital or crystal wave function for an electron by these combining these linear combination of atomic orbitals? So let me phrase a question here then. Can I form a crystal orbital, or what I can call is a crystal wave function for an electron by linear combination of atomic orbitals? And since it's a periodic potential, so the wave function must satisfy Bloch theorem, right? Those who have read about the Bloch theorem in the basic condensed matter, they know that in a periodic potential, the wave functions do have a particular form, and your wave function should satisfy the periodicity of a system, right? So in this case, let's take a 1D chain. I'll just take 1D chain of atoms. So this is one atom, another atom, like this, and this is infinitely large. So I've drawn here, but there are atoms on the left and there are atoms on the right. Both sides is there. I'll write the wave function, which is inspired from the Bloch theorem, which will be psi kx is equals to n is the number. So this is, for example, say n is equals to 4, n equal to 3, n equal to 2, n equal to 1, n equals to, I should, okay, let me call this one. These are some number. So this is n, let me call it n equals to 101, 102, and 103, 104, 105, and there are so many which are there on the left. They are starting from minus infinity to plus infinity, they are going basically. So n is from minus infinity to plus infinity, and then you have your e to the power I k n a, and phi your atomic orbitals x minus n a, where Na is the position of your atom. So the distance between these two is A, where Na is equals to position of atom. Now, your psi k x plus A, what it will be? You have to test your Bloch theorem that psi k x and psi k x plus A should differ only by a phase factor which comes in the front, and to the power minus infinity to infinity, e to the power I k n A phi atomic x minus n. Instead of x, you should write now x plus a minus na, and you can rewrite it if you just do like this: n equal to minus infinity to infinity e to the power I k n a, and you can write phi atomic equals to x plus x minus n minus 1a, right? And since n is infinity, so you can essentially take it to be n minus 1, which is starting from minus infinity to plus infinity e to the power I k n minus 1a. You can replace phi atomic, and if you replace n minus 1 with this thing, so it will be n minus 1a, right? So what essentially it is, so your n goes from n minus 1 goes to minus infinity to infinity, and you can bring your e to the power I k a outside, right? You can multiply and divide. So if you just do this mathematics, you can essentially this equation and this equation, they are same. If you just do the mathematics, and if you compare equation 1 with equation number 2, what it says that psi k at x plus a is nothing but e to the power I k a psi k x, right? And this satisfies the Bloch theorem. So our first criteria is met, satisfies the Bloch theorem. Whatever this trial function which we are talking about, that e to the power I k na and phi atomic x minus na, this satisfies the Bloch theorem. Now, having said that, we will use this wave function psi kx in the tight binding model. And how will we use it? So we have this psi kx, which is going from n equal to minus infinity to infinity, and e to the power I k n a, and phi atomic orbitals x minus na, right? Now, knowing the wave function and you know the Hamiltonian of your system, you can estimate the corresponding energy. Corresponding energy. You can easily estimate the corresponding energy, and that corresponding energy will be Ek psi k Hamiltonian psi k. The expectation value of your Hamiltonian normalized by the wave function. So with this one, you can easily compute the energy. So what you are doing essentially, you have the electron which is bound to your atom in tight binding model. Then you are bringing more of such atoms closer to each other, so that now the electron starts delocalizing, the energy band forms, and you have the wave function of your system. Knowing the Hamiltonian form, you can estimate its eigenvalues, the expectation value of the energy, and that will give you the band dispersion, that how the electrons will be behaving in presence of, and as a function of energy, basically. So now we'll calculate the Ek using the tight binding wave function, right? And where psi k and psi k is a normalized wave function, basically. So we just rewrite it this one. So this Ek we have written, where psi kx is a normalized wave function. In that case, the bottom of denominator will be having value 1. If that's the case, what does it mean? You have your wave function with over your sample length psi k star, psi k dagger psi k x dx will be equals to 1, basically, right? And your psi k x is nothing but, you can write it as like e to the power I k s and u k x, right? Where UK is a normal, UKX is normalized over a cell, essentially. So what it means, over a cell where UKX is normalized over a cell, means you integrate it over the full cell, UK star, UK dagger X, UK X equal to 1, and This implies your wave function psi k star, or dagger you can say psi k x. This star means it's a complex it's a conjugate of psi k x over length L and over n cells. What this essentially gives is, let's take a Cn in your front and e to the power minus ikx uk star x e to the power ikx ukx dx is equals to 1. So these ekx will go and cancel each other, and this is our length L and the system N, and uk star uk is what? Essentially 1, right? When you say they are normalized over a cell. So over one cell, they are 1. So this gives you Cn square summation over N, because you are having over N cells, and in over N basically atoms, and in one cell you have over one cell your UK star X and UK is already normalized. So this has a value of 1, we know, right? This is what we define. Now, if you sum it over n, what it will be? Cn square times n will be 1. So your value of your Cn will be 1 over square root of n. So your wave function essentially boils down. So I should write here Cn actually. Yeah. So your wave function essentially boils down to psi kx equals to 1 over root n e to the power I kx ukx, where uk is normalized over one unit cell, e to the power I kx is just a phase factor, and 1 by square root n is normalization factor. Now, this you can write it over, this is my equation number 3, and this is my equation number 4. Substituting, okay, and this is my, so I can compare equation. So here, whatever your UKX you are saying, it's essentially phi atomic, which we have discussed. So compare equation 4 and 3. What you will get will be psi kx is equals to Cn summation over all from n minus infinity to plus infinity e to the power I kna phi x minus na. Right? Now, here also you can do the same exercise over the atomic orbitals. And what do I mean by atomic orbitals? I'll just explain that to you. So this is your psi kx. Similarly, you can take complex conjugate of it and multiply with the psi kx. So you will be having psi k star x, psi kx is equals to modulus of Cn square, Cn times its conjugate, then over m cells or n cell, because now the counting can start, because these are two independent now, right? And it will be e to the power I k minus m plus n a, and phi star means the conjugate x minus m a phi x minus n a dx. This will essentially give you Cn square summation over m summation over n e to the power I k minus m plus n times a, and integration over this summation you can write as this phi star x minus ma phi x minus na times dx, right? This will be over all the states which are there. So phi star x minus ma phi x minus na dx, right? Now let's just draw the wave function corresponding to each atoms. Then we'll come to know how to deal this part, because this is easy to deal with. but the which you see on the right most, the integral, what will the value of this integral? This becomes very, if you take some assumptions like how, and if you know the wave function forms, that how do they fall for atoms from the quantum mechanics, we know, right? They are the Gaussians. So for each atom, this is my mth state, this atom, and this is my nth state. So it will be like this. It will be like this here. What I am drawing? I am drawing, this is phi x minus ma wave function which is localized at ma, and phi x minus na, right? Now, since these two wave functions are having finite value near the atoms only, and apart from that they go to zero. So when m is equals to n, in that case only, the phi star x minus ma and phi x minus na for m equal to n will be having value 1, otherwise will be 0. That's the condition of the orthogonality. So basically phi star x minus ma phi x minus na is nothing but delta mn. What does delta mn mean? For it will be having value 1 for m is equals to n, will be having 0 when m is not equal to n. That's what it means. And that essentially gives you that your wave function will boil down to Cn square, if you see, C capital N square, summation over m, summation over n, which is essentially the same thing, mn and n, and e to the power I k minus m plus n a times delta mn, right? And for m equal to n only, this is true. So what does it mean? It simply means that it's Cn square summation over n. This value will be, for m equal to n, this will be 1, right? And summation over all n number of atoms is what? Total number of atoms. So this will be Cn square times capital N will be 1. This gives you normalization factor to be 1 by square root of n. Now you have the wave function ready with you. So neglecting all, so what we did, we neglected the overlap between the atomic wave function on two different atoms, right? That's how we got this normalization constant. Now we can write our wave function psi kx as 1 by square root of n summation over all the states from minus infinity to infinity e to the power I k n a and phi x minus na. What is the expectation value? Expectation value will be ek psi kx Hamiltonian here, and then psi kx. And first is bra, second is the cat. So if you substitute the values of the psi k which we have derived on the above, what you will get will be 1 by n summation over m summation over n e to the power I k minus m plus n times a, and then phi x minus m a h phi x minus n a, right? And I can have this Hamiltonian for uh, m is equals to n and for m not equal to n, right? Currently there is no relation between m and n, but I can divide this equation in two form: when m is equals to n, when the wave functions will also be orthogonal, and in the case when m will not be equal to n. So I can rewrite this equation: ek is 1 by n, m is equals to n, and phi x minus ma h phi x minus ma. This is one part. The next part, I also can divide it plus 1 by n when m is not equals to n. And this summation is over m and n both. This summation is over m, this summation is over n, and m is not equals to n. It will be e to the power I k minus m plus n times a psi x minus ma Hamiltonian h I x minus na. Remember, here we can't delete those terms delta mn because Hamiltonian has some factor which will enhance the superposition because of the potential, which I will discuss. So we can't just simply ignore the second. So I will just this will be the first term, of course, first term, and this will be the second term. Now it depends on the type of Hamiltonian, what type of Hamiltonian it is to determine the energy. Now, we generally know that the Hamiltonian can be written here. H is nothing but minus h bar square by 2m del 2 by del x square plus Vx, right? And since Vx is a periodic potential, so Vx will be equals to Vx plus Na, right, in periodic potential. Yeah. And psi x is atomic orbital which satisfies this linear combination of atomic states. So if I draw the potential, for example, I had this one. So if I start drawing the potential, it will be these are my black are my atoms, and then I'll be having corresponding potential profile which will be at atoms. It will be negative. It will be large negative, signaling that the electrons are bound close to these atoms, and that's how they have this negative potential. And in the signal overall, because of this, because there will be a linear combination of atomic orbitals, because of that there will be this potential modulation, and that potential modulation will look like this. Near the atoms it will be peaking, and then this will be the potential modulation delta Vx I will call, right? So whatever this red one I have drawn, so this is the overall Vx. Earlier there was, I can draw this this delta Vx which you are seeing. You can ask that, okay, in respect to what? So in respect to the single ion potential. So single ion potential will be like much sharper. So it will be like this. It will be much sharper. So green is single ion when they were non-interacting. Red is an overall Vx, and blue is difference delta Vx. Okay, if so, potential difference substantially in the interstitial region. Otherwise, it's not very varying, but in the interstitial region, it varies a lot. And then in that case, you can just simply write our terms as, so. We'll first solve the first term solution, right? So we had defined here the first term and the second term. So this is the first term solution, which will eventually come to be 1 by n summation over all m, because m is equals to n here in that case, and 0 to L phi star x minus ma minus h bar square by 2m del 2 by del x square plus Vx potential, and then phi x minus Ma and dx, or the integral is there. Now, your Hamiltonian, if you take, right, and you, this is your Hamiltonian, if you put it on psi x minus Ma, what it will essentially give you? It will give you your energy of your atomic orbitals times phi x minus Ma, right? This is what it will give you. And essentially, this is nothing but 1 by m, 0 to L, and phi star x minus Ma, epsilon atomic, phi x minus Ma. But phi is already normalized. So what it will give you? It will give you 1 by n, sum or all m, 0 to L, it's 1, and Ma is less than equals to L. So this will give you 0 to L times 1 times epsilon atomic. It will be, so this term will be having n times epsilon atomic, which is divided by n. So this essentially gives you epsilon atomic, right? This is the first term solution. Now comes the second term solution. First was easy because your m is equals to n, so they are orthogonal, and then it's very easy to solve it for the first. But now for the second one, your second term is what? 1 by n, sum over n, where m is not equals to n, and e to the power ij minus m plus n times a, phi x minus ma, Hamiltonian phi x minus na. Now, in this case, there are these two terms, phi, or phi dies exponentially, right? So del 2 psi by del x square will be proportional to phi. And we know that phi and our uh, phi x minus ma and phi x minus na for m not equal to n is 0. So the first term of the kinetic energy corresponding to the kinetic energy, that goes to 0. So generally, phi's are e to the power minus alpha x. This implies del 2 phi by del x square is proportional to phi x minus na. This is x minus na. And since we are assuming that there is no significant overlap between the adjacent orbitals, since we are assuming no significant or overlap between the atomic wave function, it is similar to what we did for the normalization. This implies for m not equals to n, phi star x minus ma minus h bar square by 2m del 2 by del x square and phi x minus ma dx will be equal to 0, right? But what about the potential term? But what about potential term? Since potential is significantly high in this region, right? the delta Vx is not 0. So if you see Vx by x minus Na dx, although we have neglected that the phi x minus ma and x minus na for m not equal to n, they are not overlapping and they are 0, but some fraction of overlap is always there, right? And since this potential is there, because of this potential the contribution will come. So we will now allow the electrons to hop to the nearest neighbor. What do we mean to allow so the electron can hop from now here to here either, or here to here, or back and forth also it's possible, right? So that much we allow for the nearest neighbor, and we'll see how your electronic spectrum changes, how your energy changes. So we allowed the nearest neighbor hopping, allowing nearest neighbor hopping, which is in which we say that phi star x minus ma potential Vx phi x minus Na is not equal to 0 for n is equals to m plus minus 1. So the nearest neighbor they can jump on. So if you do so, you write your Hamiltonian 1 over n m n e to the power I k minus m plus n. So this is your second term, phi x minus ma, your Hamiltonian phi x minus na, right? Now, since we have defined like which terms will survive and which will not, so this tells you that 0 to L, in 0 to L, phi star x minus ma times Hamiltonian phi x minus na will be into dx will not be equal to 0 for m equals to plus minus 1, uh, n equal to m plus minus 1, n equals to m plus minus 1, 0 else, right? If that's the case, in since the first term of this Hamiltonian we have discussed, the kinetic energy goes to 0, but the second term, which is phi x minus ma, the potential delta Vx, which is large, phi x minus na will not be equal to 0. Large, this is large between two atomic sites. Two atomic sites, right? And now if you write the nearest neighbor approximation, you define this term, the full term for m is equals to plus minus n, m equal to n plus minus 1 n, to be the hopping parameter, and that hopping parameter you call to be the t. Okay, let's call it the t. So this reforms the equation number, what we are calling, let me call this one equation number 5, right? This reforms the equation number 5, and now we call the equation number, okay, let's then define that this leads to 0 to L. What will be the hopping parameter if it hops from nearest neighbor? H phi x minus na is equals to dx will be equals to t, where m is equals to n plus minus 1. Simple, right? Now this reforms the equation number 5. and this gives 1 by n mn m is equals to n plus minus 1 e to the power I k minus m plus n a, and then phi x minus ma Hamiltonian phi x minus na, right? So this term you can write, this t is hopping parameter, hopping parameter, 1 by n summation of just a second, there's a power cut here. Yeah, sorry for the delays. There's a power cut here, so because of that, there was some issues. Yeah. So we were here. You defined the hopping parameter, and yeah, so this can be written like e to the power I k for m equals to n plus minus 1. If you do it, it will be I k a plus e to the power minus I k a times t, right? The hopping parameter t, and this gives you 1 over n times, since it will be all states. 1 second. Yeah. So 1 by n times, if you do the summation, it will be over n, and then you have 2t cos ka, right? And this is essentially boils down 2t cos ka. This is the second term. This is the answer of the second term, right? If you combine your total Hamiltonian form, which was like ek equals to 1 over n summation of all m and n here a number your atoms e to the power I k minus m plus n times a. Then you have psi x minus ma, your Hamiltonian I x minus na. So the first term is nothing but the energy of your atomic orbitals. That's just a constant. That's not a function of k, uh, the momentum. But the second term, if you see, is a function of momentum. It's 2t cos ka. It's a function of momentum k, and now the gaps and things will open up. If you plot the dispersion, basically, if your t is positive and t is negative, so if you plot this dispersion, you will see how the gaps open up. And so your first term is constant, but if you plot your energy versus k, E versus k, 1 second. Right. So the first one, if you start plotting, it will be somewhere like this. And if your gamma is positive, then it will be something somewhere like this. So this is the point of your minus pi by a. This is the point of your plus pi by a. These are the Boolean zone, from the condensed matter, basic condensed matter course. And this is for gamma less than 0. This is for gamma greater than 0. And this shows that the band opens up near the pi by a, the band reconstruction is near pi by a. So this is for the 1D. Now similar can be done in the 2D also. So for 2D, square lattice this will eventually be your the atomic terms will be there as it is ek. So there will be at constant atomic terms, atomic energy. Okay, that will be constant plus 2t. If I am assuming the hopping is symmetric in all the direction, cos kxa plus cos kya and in 3D it will be cos kxa, cos ky, and cos kza if it is symmetric. Otherwise, it will be 2t1 cos kx a1 plus 2t2 cos ky a2, 2t3 cos ky a3, depending on the direction of the hopping, because they can be different in principle. So this is what the tight bonding is about. So we started with saying that okay, the atoms are the electrons are closely bound to the atoms. We bring the atoms closer to each other. That leads to the formation of these atomic orbitals, linear combination of atomic orbitals, and we come to the derivation of this, how this band picture evolves. And you see that okay, the band it's essentially like the chronic panning model where the band gap opens up at the minus pi by n pi by a, where the hopping parameter t governs this one. You can also take the next nearest hopping term also, but the contribution from that term will be very less, since already the overlap is very minimal between the atomic orbitals. But for the more of the precision of the results, one can take next nearest, next to next nearest atomic orbitals, and that eventually gives you the better results. But the next nearest then hopping is also good enough to work with. Now, having said that, we will move on to the next part, which I said that I will discuss with you, is in this core of coursework, is introduction to the graphene, right? So this is what I promised you. So I'll cover that one also. Yeah. So the graphene, it's a 2D material, and which was first discovered. Okay, so I'll just uh, tell you very briefly. So why graphene is important? Why we should pay attention to the graphene? Right. So let me just write it here. Introduction to graphene. Let me just write here. Introduction to graphene. Yeah. So in the early 90s, like it was Pierre Wales who first wrote on the paper, who first wrote the band structure of the graphene and showed that unusual semi-metallic behavior is there in this material. Although at that time, one could not actually look for this material, and the reason being very simple, because it was 2D material at the time, the discovery was not there, and there were theory also that it won't be possible, right? So, but this theory of the whales in 1946, PR whales, PR whales. Look at the time durations. It came in the 1946. He wrote on the band structure of graphene. In 1946, he wrote the band structure of graphene. But since graphene was not readily available at that time, it was there available, but the single layers we were not able to exfoliate or find and do the patterning in the contacts on those ones. So people started using. So they were, but eventually they were using these graphites for the nuclear reactors, and his theory was very useful in those cases. So at that time, the thought of this purely 2D structure was not reality, and Wolf's studies of graphene served him as a starting point to study graphite, an important material which was their use for nuclear reactor in the World War II. And uh, that's how the study of this carbon-based system started. But what is the exciting part about the graphene is exciting part about graphene. It is the first 2D material which was observed in 2004. So it's the first 2D material which was experimentally realized Otherwise, earlier before that, there was quasi 2D, two-dimensional electron gas, all those things people were making, but they were not perfect 2D. This atomically thin single sheet of carbon arranged in a honeycomb lattice. So one of the most interesting aspects of the graphene is that its low energy excitations are massless. Low energy excitations are massless. One thing, they are chiral. They have the chirality. The backscattering is very minimal chiral in nature. They are Dirac fermion. Dirac fermion means the dispersion instead of being parabolic, it's linear. In neutral graphene, the chemical potential crosses exactly the Dirac point. This particular dispersion that is only valid at low energies. This mimics the physics of quantum electrodynamics for massless fermion, except for the fact that graphene uh, fermion moves at a speed which is 300 times less than the speed of light. Graphene Dirac fermion moves at a speed Vf, which is 300 times less than speed of light. What is the Fermi velocity in the graphene? It is 1 into 10 power 6 meter per second. And what is speed of light? It's 1 by 300 of 3 into 10 power 8 meter per second, which is speed of light. That's what it means. And then there is a large gap, the cyclotron gap, in case of this quantum hole. So you can observe this integer quantum hole effect at room temperature. That's what also predicted in 2007 by Geim's group, Norslow and Geim. And all those things were there. So this is about the graphene. It has honeycomb lattice. It shows these peculiar properties. All good, all well. But in the recent past, what has been done is like you can take two layers of the graphene, two single sheet of atoms. You can put them on top of each other and can rotate them slightly. That generates the another periodic potential in the system, and those Hofstadter spectrum, all those things of these superlattices which can't be realized at the these Hofstadter spectrum requires for the graphene requires around 10,000 Tesla to realize that physics, to see that physics. But just by twisting the two layers with respect to each other, you can realize that physics even at 1 Tesla of magnetic field. That's achievable with the superconducting magnets. Another fact is like graphene itself is a semi-metallic, but when you twist it with respect to each other, it shows peculiar properties like uh, superconductivity in twisted bilayer graphene at some particular twist angles, like magic angle to twisted bilayer graphene I'm talking about. Then if you put the graphene on HBN, HBN is also honeycomb lattice that also generates these Moire potentials, periodic potential. That also reconstructs the band. And in that case, you see exotic physics like the Chern insulator in absence of magnetic field that emerges from the band curvatures, like the Berry curvatures of the system. So this system itself, the graphene itself, has given a lot of validations to the different theories which were lying in the market for years and has shown a path in which direction of the physics we should think and which laws assumptions are valid for the quantum mechanical systems. So this is these discovery of the graphene and study of the graphene has been a fundamental aspect of studying this quantum mechanics, whatever we have developed the theories over the years, is a system where people were able to test it, were able to engineer the system, knowing how these lattice bond length, all those things change the parameters of the band dispersion. They were able to engineer the system, which a transistor basically, which can act like a superconductor, which can act like a Mott insulator, which can act like a metal, which can act like a ferromagnet, which can act like a ferroelectric system. All those things are there in one system, graphene, just by tuning the gate voltage. You change the gate voltage, your system will go from metal to insulator, metal to ferromagnet, metal to maybe Chern insulator, So there are different phases in which you can tune just by tuning the gate voltage, applying gate voltage in the system, and of course by tuning some twist angles in the system. And that's why it's become very important, very important to understand the electronic dispersion of the graphene, to understand the tight binding models of this graphene, which eventually gives rise to this exotic physics. So having said that, I will just show you what the bands, how the structure of the atoms are there in the case of the graphene, and what the K value, the values which we talk about very often in case of graphene, K and K prime value, which basically are the two non-equivalent points of the dispersion, basically. So in case of graphene, your atoms are carbon. It's made up of only carbon, right? So you have your structure like this. You have one atom of carbon here, one atom of carbon here, and one atom of carbon here. Similarly, you have, okay, let me just draw hexagons first. I'm not able to draw the perfect hexagon, but okay, let me just draw the best possible which I can. Yeah, so this is one hexagon. Similarly, you can have another here. You can have another like this, and at each corner of this, your carbon is sitting. So one carbon is sitting here, one carbon is sitting here, one carbon is sitting here. No, one carbon is sitting here, and one carbon is sitting here. One is sitting here, one is sitting here. This is what a triangular lattice. But on the other side also, there's a carbon sitting here. So this green and black are both carbon, but why I have drawn them in the different color? The reason being, graphene itself is not a Bravais lattice. It's made up of the two Bravais lattice. One you can think like A sublattice, black one, B sublattice, green one. So let me call the green one as the A sublattice and the black one as the B sublattice, right? And this is your system. And now, since brevilatись is like you can translate from one point to another, that's what by translation vectors. But in the case of the graphene, you can't do that. You have two brevilatys which are intersecting at an angle of 120 degree, and that's what it is. So now, if I I have to define the vectors, the lattice vectors in this case, how they would be? They would be like these ones will be your lattice vectors. So this will be your A1, this will be your A2, and similarly. And the unit cell, if you have to draw, it will be somewhere like. So this unit cell is comprised of two atoms, one green in the center, and one fourth contribution comes from each of these atoms on the sides. So that essentially gives you the part of it, like the two atoms per basis. It won't be till that point. It will be just somewhere. Yeah. So this is right. Now, if I have to uh, write in terms of, okay, I'll just define the lengths. So this A is the distance between the nearest carbon atoms. So if that's the case, then A1 and A2 can be written as A by 2, 3 root 3, and A2 can be written as A by 2, 3 minus root 3. Now, where A is A is like actually 1.42 angstrom. It's carbon distance. So whatever I'm following here is from the electronic properties of graphene by this uh, A.H. Castronetto and Casno's law and Andregain. And there are other additional authors also. So the electronic properties of graphene. This is the paper which I'm following. If you are interested in more reading about it, you can just have a read of this paper. It gives you a brief history of the graphene and what are the phenomena, key phenomena which are related to the graphene. So is the carbon-carbon distance. Now you can of course calculate your the reciprocal lattice vector. Reciprocal lattice vector, we know that B1 is related to 2 pi A2 cross A3 by A1 dot A2 cross A3. That's how they are related, right? So here you A3 you can take it to be one z cap basically. So these are x, y, and then this will be 0, 0 z cap. If you do so and you calculate your B1, will essentially be 2 pi by 3a, 1 square root of 3. Since it's a honeycomb lattice, your Brillouin zone will also be a honeycomb lattice, 1 minus root 3. And if you draw this your B1 and B2 vector, they will, if you draw these two vectors, so you can see that in the x position they are at the same point, but in the y they are just opposite to each other. So if I ask you to draw this one, it will be somewhere like this, and this is your kx, this is your ky. So b1 b2, so these are kx and ky components of it basically. And if I ask you to draw b1, your b1 will be somewhere here and your b2 will be somewhere here, right? And if one asks you to, okay, then how would you make the Boolean zone of it? You take the intersection of your b1 basically. That's how you do, right? You intersect this one, your line. Here also you intersect the line. Similarly, you will do here also, this line also. Similarly, you do this line also. Similarly, you do this line also, and similarly, you do this line also. And this is your Boolean zone. Here, the center point of the Boolean zone is known as the gamma point. Corners are known as the K, and this corner will be called K prime. Although they look similar, but they have the different uh, physics associated with them. K and K prime. These K and K prime are known as the Dirac points or the valley. The central point is known as the M point, and this one is your B1. This is your B2, right? And your Boolean zone, your unit cell will be like this. This B1 and B2. Now, if one asks you that, okay, what will be the coordinate of K1 and K2? So K1, of course, you can write that, okay, K1 will be nothing but you just B1, uh, this is B1 plus 2B2 divided by B1 minus 2B2 divided by 3, and another will be just the opposite of it. So you can just uh, solve it, and they can be written in the form yeah. So your k points can be written is like your k1 can be written as 2b1 plus b2 by 3, right? And your k2, k1 and k2, I mean the k and k prime, b1 plus 2b2 by 3. So this is k2 is essentially k prime, and this K1 is essentially K. So if you do so, what you will get is K will be nothing but 2 pi by 3a, 2 pi by 3 root 3a, and K prime will be 2 pi by 3a and minus 2 pi by 3 root 3a. That's how your K and K prime are there in case of the graphene. Other 6 coordinates are also, they are equal. They can be translated. I will just draw this point, this point, and this point. They are of the one kind. This point, this point, this point, they are of one kind. You can just translate them with the rest, with the Breve lattice vectors basically. So here, essentially, you have two non-equivalent point K and the K prime, and from there only the band emerge. The band touches at those points, and that's why they are known as the Dirac point. Then that's why they are known as the Dirac point, because at these points the band dispersion is linear in nature, Dirac-like, and these K and K prime are known as the valley of the system. Yeah. What's next I have to discuss? So this is about the introduction of the graphene and the Dirac points. The next I had to discuss is, I think, the tight binding model of the graphene. I'll just discuss that one also. So the tight binding dispersion of the graphene. Sure. Let's cover that one also. Yeah. Tight binding dispersion of graphene. So you have seen in the tight binding model that first is atom to atom, that gives you the atomic energy. But then if you have to see the band dispersion in form of the wave vectors k, then in that case you have to account for the nearest neighbor hopping energy, then next to next nearest hopping energy, all those things require. So in the case of the graphene, in this lattice, you can define the nearest neighbor, right? For example, in reference to the central atom B, this atom B here, you can define your mm, nearest neighbor. So this is your delta 1, this is your delta 2, this delta 3, and this is your delta 2. And you can write down the coordinates of it, and then whatever we had derived, similar here only, in the form of the creation and annihilation operators, the tight binding, same tight binding model, nothing different, and you'll get the tight binding results for the graphene. So the delta 1 coordinate you can write as a by 2, 1 square root of 3. Delta 2 is a by 2, 1 minus 1 and minus square root of 3, and delta 3 here will be minus a 1 0, right? And this is the nearest neighbors, nearest neighbor coordinates, 3 atoms, right? Now what about the next nearest? What are the coordinates of next nearest in case if you want to solve? What about next nearest? Yeah, so the next nearest are 6. They are 6. What are the coordinates of them? Delta 1 prime will be plus minus a1, delta 2 prime will be plus minus a2, delta 3 prime will be plus minus a2 minus a1. Where are they? So they are these ones. 1 second. These ones. The next nearest of this next nearest is this one. This one. This one. 3, 4, 5, 6, these black atoms, they are the next nearest. Hope. So there will be different what is a hopping parameter for the nearest and the next nearest. So the Hamiltonian you can write. So we have to write the Hamiltonian, right? So the tight binding Hamiltonian for electron in graphene, the tight binding Hamiltonian for electrons in graphene, considering that electron can hop to both nearest and next nearest. If you don't want the next nearest, just put the t prime equal to 0, or just delete the next nearest neighbor term atoms. Right? Here we are taking h bar to be 0. So Hamiltonian will be minus t, that's the nearest neighbor term, ij sigma. Whenever I am taking the ij in this bracket, it means they are the nearest one. J is can be I plus 1 or I minus 1. That's essentially it means sigma I. Sigma is the spin here. And this dagger B sigma J, and the Hermitian conjugate of it to make this it real. And then you take the next nearest, so you put these two of the brackets. That's what it means when I'm doing these two of the brackets here, over the spins, and A sigma I dagger A sigma J plus B sigma I dagger B sigma J plus Hermitian conjugate of it, where so I see I discussed the creation and these there are two sublattices A and B, right? So A I sigma and A I dagger sigma are basically annihilation and creator operators. Annihilation. Annihilation mean removes the electron from there, and A dagger creates an electron with. So you can drop actually the sigma term spin. It's not relevant at the point. With spin sigma, it can be sigma can be either up or down. On site Ri, on sublattice A. For sublattice B, we have B dagger or B sublattice A, and the T for the graphene is 2.8 electron volt approximately. Nearest neighbor hopping energy. Hopping energy. And T prime is the next nearest hopping energy. And if you just solve this Hamiltonian, what you will get, essentially, I'll just write the final results. It's plus minus t, where t is the hopping term, 3 plus function, which is function of k, minus t prime, function of k. Plus minus means the bonding and the anti-bonding, basically, the one which we discussed. Right? And in where fk is nothing but 2 cosine root 3 kya plus 4 cosine root 3 by 2 kya in multiplication of cos 3 by 2 kxa. And if you check at the Dirac points, the essential value of your energy will go down to 0 at those points. If you compare your Fk value at the Dirac point will be minus 3, that eventually will give down to uh, your E plus minus K will be equal to 0 at those points. So where the plus minus applies for the upper and the minus applies for the lower pi band basically. And mm, it's very clear when T prime is 0, the dispersion is symmetric in electron and hole, and when T prime is not 0, then the dispersion is not symmetric, and you can expand it actually near the K points. So dispersion can be expanded near K points. Dispersion can be expanded near K point. Your small k will be capital K plus Q, where this K is Dirac point, and here Q is less than K, capital K. E plus minus Q is nothing is equal to plus minus VF Q. This and the order of Q by K square, but this term is negligible. And if you see this one, so E plus minus is H bar K VF you can write H bar VF K dot sigma plus minus. So here if you see, your dispersion in energy is linear like this, E versus K. And remember, this is similar to E is equals to PC. If you draw for the photons, this also has the similar one, right? The energy. So, but here your VF is 1 by 300 times your speed of light. So you essentially in the graphene mimics the quantum electrodynamics, and those theory which were developed for the quantum electrodynamics have been tested in the case of the graphene, and it has been shown that okay they are valid here, and so the relativistic effect you can study in this condensed matter system. No one would have thought that this would happen, but see that you never know what will emerge. So your VF is essentially 1 into 10 power 6 meter per second. So this is about the graphene tight binding model, and uh, the Dirac point I have discussed, how the Dirac point lies, the nature of the bands near the Dirac point also I have discussed. They are linear. The so this one we have discussed. Introduction to graphene, tight binding model designs, and the density of state of the behavior. This you can read from the paper which I have discussed, which I'm referring to. The paper name is the electronic properties of graphene. Properties of graphene. It is like review of modern physics. Volume 81, January March 2009. Jan March 2009. The author is A.H. Castroneto. He is from Boston, Massachusetts, USA. And then K.S. Novoselov and Andre Geim are also there in this paper. They are from University of Manchester, UK. And you can read this paper. It's a good read on the graphene. You will get more of insights on the electronic properties of the graphene, like the Klein paradox, the chirality nature, less of the backscattering, localizing, anti-localization in case of the graphene and the bilayer graphene. So this will give you a better understanding about the system. And the density of state, you can also see that it goes linearly uh, as a function of energy, and then there are Benhoff singularities, all those things are there. You can read more about it. And if you have any doubt or comment, you can ask me in the comment section. I'll be happy to address your concern. And the two-dimensional and the electrons in the 2D periodic in the periodic potential and the magnetic field has been discussed in the class by Professor uh, Saurabh Basu. So you can follow those lectures. It's essentially the same thing, which I would have thought. So it's the class of the quantum Hall effect by Professor Basu. There you can go and have a look at it. And with this one, I will conclude the class. If you have any question, doubt, suggestion, you can ask me in the comment section. I will be happy to address your concerns.